From the dawn of human curiosity, the stars have beckoned us, distant, glittering beacons suspended in the cosmic night. We look upward and wonder, how can we reach those far-off worlds? How can we cross the unfathomable distances that separate us from the nearest suns? The speed of light, as the fastest speed known to physics, presents an imposing wall. At nearly 300,000 kilometers per second, it's swift beyond everyday comprehension, yet it still leaves interstellar travel out of reach for a human lifetime. For centuries, this barrier shaped our imagination. Faster-than-light travel was relegated to myth and legend, a fantasy confined to the pages of science fiction novels and the dreams of visionaries. But as physics advanced, a startling possibility emerged, not by breaking the cosmic speed limit, but by bending space and time itself. This was the seed of the warp drive idea. Rather than moving through space faster than light, what if we could move space around us, compressing the space ahead, expanding the space behind, effectively riding a wave of warped space-time that propels us faster than light without breaking the fundamental laws? This concept, once only a fantastical dream, ignited hope that humanity might one day cross the stars, visiting distant solar systems in the span of a human generation. But is this dream rooted in reality, or destined to remain forever out of reach? The warp drive's conceptual leap came in 1994, when physicist Miguel Alcubierre formulated what is now known as the Alcubierre drive. Using Einstein's general relativity equations, he described a theoretical model where a spacecraft could sit inside a bubble of flat space-time, with the fabric of space contracting in front of it and expanding behind. This bubble, essentially a ripple in space-time, could move faster than light, not because the ship itself exceeded light speed locally, but because the space it occupied was being dynamically reshaped. This was a revolutionary insight. It respected Einstein's cosmic speed limit by redefining how motion occurs. However, the initial models revealed an enormous hurdle. The energy required to create such a warp bubble was mind-boggling. Early estimates suggested that you'd need an amount of energy comparable to the mass energy of an entire planet, or even a star, converted to exotic negative energy, a concept not yet known to exist or producible. Additionally, the theoretical warp bubble depended on exotic matter, substances with negative energy density capable of bending space-time in unconventional ways. While quantum physics hints at negative energy effects, such as the Casimir effect, generating and controlling these at scales required for warp travel remains purely hypothetical. This tension between elegant theory and impractical demands kept warp drive locked firmly in the realm of theoretical physics for decades. Yet, science is never static. As physicists re-examined Alcubierre's model, new mathematical tweaks suggested the energy requirements might be dramatically reduced. By altering the shape and properties of the warp bubble, creating thinner walls, or varying bubble geometry, researchers found ways to potentially reduce the exotic matter needed by orders of magnitude. This shift sparked renewed excitement and scientific curiosity. Even if the requirements remain large, they may no longer be entirely impossible. Organizations like NASA's EagleWorks laboratory, led by physicist Harold White, have conducted experimental studies to test warp bubble creation at microscopic scales. Using powerful lasers and advanced quantum techniques, EagleWorks explored whether space-time might be manipulated in ways that produce tiny distortions akin to warp bubbles. While the experimental evidence remains preliminary and controversial, the efforts mark an unprecedented shift from speculative theory to experimental inquiry. The warp drive has entered the scientific frontier. However, moving from equations and small-scale experiments to building an operational warp drive faces staggering obstacles. The engineering challenges push the limits of human technology and material science. First, controlling a warp bubble requires precise manipulation of space-time on unprecedented scales. We would need to generate, stabilize, and steer the bubble, all while protecting the occupants inside from immense stresses. Moreover, the energy sources required remain beyond our current capabilities. Even with reduced estimates, powering such a device demands energy densities far surpassing anything we can produce or store. Could future advancements in fusion, antimatter, or zero-point energy fill this gap? Possibly, but these remain speculative. Safety is another critical concern. Theoretical models warn that particles and radiation could accumulate in front of the warp bubble during travel. Upon arrival, this concentrated energy might be released suddenly, potentially devastating the destination environment or the craft itself. Furthermore, navigation and communication through warped space-time introduce unknown complexities. If space itself is being stretched and compressed, how does one maintain a stable course? How do instruments interpret signals that might be distorted or delayed? The challenges compound. Among scientists and enthusiasts alike, the warp drive inspires both fervent hope and deep skepticism. Visionaries see it as the key to the future, a technology that could catapult humanity from a single planet-bound species to a multi-star civilization. This vision promises an era where humans explore far beyond the solar system, unlocking secrets of alien worlds, cosmic origins, and even the fate of the universe itself. To them, warp drive represents the natural next step in exploration and discovery. But many scientists caution that these hopes may never materialize. The laws of physics as we understand them might forbid such travel or impose limitations we have yet to uncover. They remind us that extraordinary claims require extraordinary evidence, and so far, the evidence for practical warp travel is lacking. History is filled with tantalizing ideas that never panned out. Yet, it's also filled with breakthroughs that once seemed impossible. Beyond science, warp drive holds a special place in human culture. From the earliest radio dramas and pulp magazines to blockbuster films and television series like Star Trek, warp speed has captured imaginations worldwide. This cultural imprint is more than escapism. It shapes how society perceives space exploration and future technology. Warp drive is a metaphor for boundless possibility, a promise that the universe is within our grasp if only we dare to pursue it. Through stories, we prepare ourselves mentally and emotionally for the challenges of interstellar travel, inspiring generations of scientists, engineers, and dreamers to push beyond the limits of the known. Today, the warp drive idea stands at a fascinating juncture. It is part rigorous science, part hopeful speculation, part cultural mythos. Advances in quantum physics, gravitational theory, and energy technologies may one day tip the balance from theory to reality, or new discoveries may reveal insurmountable barriers. But the pursuit itself is a powerful catalyst, driving new physics, stimulating technological innovation, and expanding humanity's vision. The journey toward warp drive is as much about the human spirit as it is about propulsion physics. It is a quest to transcend boundaries, physical, intellectual, and cultural. Warp drive embodies the essence of humanity's eternal quest to explore, to understand, to reach beyond ourselves. Whether warp drive becomes real or remains a dream, its story is a testament to our courage, the courage to question the impossible to chase the stars, and to imagine futures we have yet to live. Because in dreaming of warp travel, we celebrate not just technology, but the limitless capacity of hope. And in that hope lies the true engine of our journey through the cosmos.